In this video here, we're going to take a look at angular speed. Now, when an object is moving in a straight line, the speed, usually measured in meters per second or kilometers per hour, describes the rate at which distance is changing. Now, for an object moving on a circular path, then we can use the same method for measuring speed, but it's often easier to measure the speed by considering the rate at which the radius is turning. So we've got this diagram here, right? So what I've got here is a particle P. And the particle P then moves from this point here, point A, to point B on the circumference of radius r meters. So I've got my radius here, r meters, and it moves on the circumference of this radius, right, of r meters. Now the radius of the circle turns through an angle, theta radians, okay? So the distance moved by P, that's this particle here, is r theta meters. Okay, so r theta meters there. Sounds like a bit of a tongue twist, but there we go. So therefore, if P is moving at v meters per second with this speed here, we know then that v is equal to the derivative then of r theta with respect to time t. So that's equal to r times d theta by dt. And in that case, then we just get r times theta dot. So before we work through a couple of practice questions here, what I want to do then is just quickly summarize what we found here for angular speed. So like we just said, then let's just quickly summarize everything that we know here for angular speed. So theta dot here is the rate at which the radius is turning about O. And this is known as the angular speed of the particle about O. Now the angular speed of a particle is usually denoted by this Greek letter here, and you should recognize this Greek letter, right? This is omega. And this is measured in radians per second. So to finish with here then, if a particle is moving around a circle of radius r meters with linear speed v meters per second and angular speed omega radians per second, then v is equal to r times omega. So this final point here is a really, really important point here. So please do make a note of the final point here. You're more than welcome to make a note here of, the preceding 3 points, but this final point here is the most important point. So please do make a note of that to finish with. So that concludes this introduction here to angular speed. As we mentioned then on the previous page, right, all we're going to do here is just work through 2 practice questions. So let's just get started then with question 1 here. So let's just get started then with question 1 here. Now for this question, what we're told here is a particle moves in a circle of radius 12 meters with this speed here of 3 meters per second. And all we want to do then is just find the angular speed. So for this question here, it really is quite a straightforward question, right? But more than anything, this is just an introduction here to angular speed. And to be honest, we are kind of easing ourselves here into further mechanics too. Okay, so this topic here, angular speed, is kind of setting us up for the remaining part of this chapter, right? So as you would expect, quite a straightforward question. So what do we know here? So what we know here then is that r is equal to 12. So the radius here is 12 meters. We also know the speed, right? So we know v here is equal to 3. The only thing that we don't know then is the angular speed here. So don't forget then that we use the Greek letter omega here to represent the angular speed, right? We don't know this, okay? And that's what we want to find. So do we have a relationship here then that connects r, v, and omega? Well, of course we do, right? As we mentioned in the introduction here, v is equal to r times omega. So v is equal to r times omega. So we know r, we know v, and in that case, then by using this relationship here, we can easily solve for omega. So v then is 3, r is 12. In that case, then 3 here is equal to 12 omega. So clear then, if we just want omega here, all we need to do then is just divide both sides by 12, right? So omega is equal to 3 over 12, which just gives us 1 over 4 once we simplify, which is just 0.25, right? So to finish with here then, let's just quickly state that the angular speed here, so the angular speed is, so this is 0.25 because we obtained 1 over 4, right? So 0.25, and don't forget the units here. So we measure angular speed as radians per second. So 0.25 rad second. Okay? And there we have it then. So like I said, a nice easy question really just to get us started here. But there we have it. So this here then gives us the solution to question 1. And then finally, to finish with here, we have the very last question, question 2. Now for this question, again, just as we saw with the previous question here, it's pretty straightforward and all things considered quite easy. Now it is a little bit more challenging than the previous question, so it might take a little bit more thought, but compared to some of the later stuff here within Further Mechanics 2, this is really quite straightforward. Okay, but let's just take a look at it together anyway, and hopefully it doesn't cause too many problems. So what we're told here then? So what we're told here is a particle moves around a circle in 8 seconds at a constant speed of 12 meters per second. All we want to do here then is just calculate the angular speed of the particle and also find the radius of the circle. So where do we begin here? Well, to begin with here, I'm just going to make a quick point then that the particle, so the particle rotates for an angle of 2 pi radians because it goes around a full circle, right? So the particle rotates through, so it rotates through 2 pi radians. Let's just write this down in full. So through 2 pi, it's supposed to be pi there, 2 pi radians in 8 seconds. Now, why is this important? Well, don't forget then, the angular speed here, omega, is just simply the rate of change of the angle in radians per second, okay? And using that fact then, we can easily find omega. So omega here is equal to the angle that's formed, or the angle that we rotate through, in this case here, 2 pi radians, divided by the time taken. So for omega here, we get 2 pi, that's the angle that we've rotated through, divided by the time taken, which is 8 here. So we get 2 pi over 8. This just simplifies to give us pi over 4, right? So if we give this here to 3 significant figures, what we get then is 0.785, right? So 0.785, and don't forget your units as well, of course. So 0.785 radians per second. Okay, perfect. So this here then is to 3 significant figures. And that gives us the first part here. So what we've just done then is found the angular speed of the particle. I'll give that a tick. We've completed that part. What we now need to do then is just find the radius of the circle, right? So again, let me just make a note here. So for the radius then, so for the radius of the circle here, how do we find this? Well, all we now need to do here then, as we established in the introduction, is just use this relationship here. So V is equal to R times omega, okay? We know what V is. We're given that here. So let me just make a note then. So V here is 12. We've just evaluated what omega is, right? So V is 12 and omega is 0.785 to 3 significant figures. So 0.785 there. Perfect. And if we just want the radius here, is R, right? All we simply need to do here is just rearrange and make R the subject of the equation, and then just substitute V and omega into that rearranged form, right? So nice and straightforward then. R here is simply V over omega. So V over omega. And in that case, then R here is 12 over 0.785. So 12 all over 0.785. Put this into your calculator here. And if we round this to, say, again, 3 significant figures here, what we get then is 15.3 meters there. Okay, perfect. So this here was not the solution to the first part, right? It's just one part of a question anyway, but 0.785 radians per second, that gives us the angular speed of the particle. And then 15.3 meters here gives us the radius of the circle. Perfect. Bosh, right? Now, like I said, this question here, again, is pretty straightforward, a little bit more challenging than the previous question, but compared to some of the later stuff here within Further Mechanics 2, which we will be getting into pretty shortly, yeah, this question is quite easy, right? So hopefully As I said at the beginning of the question, this shouldn't cause too many problems. If there is anything that you're not too sure about, please just leave a comment and I will try my best to help. But there we go. So this gives us the solution here to the very last question, question 2. And that brings the end then of this video here on angular speed.